So, just did a few calculations to finish the things we did today. I just thought I'd make a quick little video to supplement lecture from today. So this is the example I worked out. It was actually section 5.7, number 15. We got this far. We calculated the determinant in class. We figured out that the eigenvalues were -2, -1, and 1. Of course, I was annoyed because I wanted a complex example. But let's, finish the example. I'll do it quickly here. So to start with, I found the eigenvalue, the eigenvector rather, for the eigenvalue -2. So I got a plus 2i, because a minus a minus is a plus. So a plus 2i, which gives me this, which row reduces to that, which row reduces to that, which row reduces to that. So if we have u1 as the eigenvector, we have u plus w equal to 0, and we have v equals to 0 from that, which if I put if I put u equal to 1, that puts w equal to -1, so I got 1, 0, -1 for my eigenvector there. And then I moved on to the next eigenvalue, alright, which I'll scooch this up here. So the next eigenvalue was, come on, paper work, and I'll scan this, of course, and post it for you guys, but here we have eigenvalue -1, so a plus I gives me that, which row reduces to that, and then that, and then that, and then that, and then that, which means that my eigenvector with eigenvalue -1 has this form, which if I put w equal to 5, I get -615. So there's my second eigenvector, all right? And it has to work out like this. There has to be one free parameter in each one of these because I have 3 distinct eigenvalues. And remember, there has to be at least one eigenvector for each eigenvalue. So like these calculations were in some sense inevitable. I had to have like one row of zeros in these calculations. It had to happen, logically speaking, because I don't have a repeated eigenvalue. That's all that could happen. And so here, this eigenvalue 1, which row reduces to that, which then putting it, the usual null space basis calculation, u equals to -w, v equals to 1/4 w, and w is w. So if I put w equal to 4, I get -414 there. So there you go. I've got my 3 eigenvectors for my 3 eigenvalues. Now what do you do with them? Well, you could do lots of different things, right? We could diagonalize the matrix. We could use that to calculate powers of the matrix. I haven't done that in class yet, but I will. But the application we have talked about is solving differential equations, systems of differential equations, right? So here is my 3 eigenvectors, doop, doop, doop. My eigenvalues, that, and that, which gives me this solution, and that solution. And so to find the general solution, I take a linear combination of those guys. That follows from the derivation that we did Friday before spring break. And so there it is, C1 times this, plus C2 times that, plus C3 times that. And then the book has asked you to comment on the stability or lack thereof of these solutions. The way it works is that if you have an exponential with a positive argument, as t goes to infinity, that thing blows up. So basically, if you had C3 non-zero, then the solution tends to infinity from this piece. On the other hand, if C3 was 0 and you just had these two non-zero, then the solution would tend to 0. So because we don't quite know what's going to happen if we perturb the solution a little bit, if you could imagine the solution starting a little way this way or that from the origin, you could go different directions. You might go to infinity, you might go to 0, it just depends. So this is an unstable equilibrium, right? I think the book calls it a saddle point. All right, so there's that. Of course, I haven't talked about stability in class at all. Let's see here. But it is in your homework, so I figured the decent thing would be at least to tell you a word or two about it before I collect the homework, right? And I will take homework questions Wednesday, of course. It's part of the reason I'm making this video, so we have time for that. So here's the example I should have done. This lovely number 17 from section 5.7, which has got these big ugly numbers in it. All right, and I decided to use x rather than lambda for the characteristic equation, just to show you how that looks. this might work better for you, some of you, like algebra-wise, just because you're more like confident using x. But again, you can't confuse this x with the x that's the solution to the differential equation, so there's that danger. But anyway, so this is not my first try. This is like my second or third try at this characteristic equation. It took me like a half hour to work this out. All right, it's not easy. It's so easy to make a mistake. But I did get it this time. I worked it out and expanded. I did a row reduction this time. I added 5 times the third row to the first row to get rid of the 10, the 30, to get this x here, right? So I added, 5 times that to that, which gave me this. And that made it a little bit nicer because that put an x here. But it did have the side effect of putting a minus 5x minus 3 here. I'm not sure it's really better. I don't know. Again, I don't know. This is just a hard problem. It's just a hard problem. All right. And so then I did this. I multiplied everything out. Then I collect like terms. All right. Collect like terms. Eventually, I get to this. And then, lo and behold, if you plug in 1, you get 1 plus 39 is 40, minus 40. 40 minus 40 is 0. So 1 is a 0, which you guys probably would have guessed if we'd done that in class, right? You guys guessed the 1 in example 15, so exercise 15. So you'd have guessed the 1 here. And if you'd done that, that would have been lovely, because then you'd know that you have to factor out an x squared and a 29. So this is what I was talking about, like the expense of not, so like I've been doing lambda a minus lambda I. Notice to do xi minus a here. The part of the cost of that is I have to remember to put a minus on every single entry of a. It's like 30 goes to minus 30, 64 goes to minus 64, minus 23, and so forth and so on, right? So I got 9 minus signs to keep track of, and I think I did it right. But that's why I don't usually do it that way. But it is nice because it does at least give you a leading coefficient which is positive. So the factoring is a little bit more normal. Otherwise, you got to factor a minus out. I mean, somewhere you have to deal with the minuses. They're there, whether you like it or not. Okay, anyway, so calculational strategies aside, we get to this. I factor x minus 1 out. X squared and the 29 are practically for free, because if you think about multiplying this out, you have to put x squared here to get x cubed. You have to put 29 here to get minus 29. But putting the minus 10 there is not obvious. I like to use long division to calculate that. There are other ways, of course, but here's the long division way. It pops out that x squared minus 10x plus 29 is the cofactor to x minus 1, which tells me to put a minus 10 here. So that's my color coding. And then I complete the square on the quadratic, which reveals that we have a pair of complex conjugate solutions, namely 5 plus or minus 2i. So these are my eigenvalues, one real and a pair of complex. That's what I wanted for today. This was supposed to be the example for today. So sorry. It's just as well we didn't get to it in class anyway, because I would have then confronted, after we found the eigenvalues, I had 10 minutes left, and in those 10 minutes I would have faced this boondoggle. Well, okay, so one of these things is not a boondoggle. It's relatively benign, which is finding the real eigenvector. The real eigenvector is not too bad. See here, a minus I, it gives me this. And you might wonder where the steps are. Well, let me show you this calculator. Check this out. So if I go mode, and I go matrix, and I go 1, and I go, 3 by 3. Oh man, it forgot them. Rats. I guess when I turn off the calculator, it goes away. I'll put it back in. 29, 64, 23, minus 11, minus 24, minus 9, 6, 15, 3. All right, so now I've got the matrix in there. It's not A, it's actually A minus I, right? All right, so I go, okay, on, and then I go, let's see here. I didn't get, am I in matrix mode already? I'm in matrix mode already. So I go shift, matrix, and I go down, check that out, roof, and then I'll go, let's see here, shift matrix, and I'll go matrix A, like so, and then I'll hit enter. And this calculator is super dusty. I just got it from Dr. Sprano. It's been sitting in his office for forever. He let me have it. Woohoo! Thank you to the student who left it there. Anyway, so if I can zoom in a bit, as you can see, that is exactly the row reduced matrix. That's how I did this one, actually. And so one thing I should have emphasized in class more, and I haven't, my apologies, is that you guys are free to use technology on these problems. So it would be most healthy for you to, use either MATLAB or whatever to do these kind of row reductions. Now, of course, you can also just rely on the website, which does everything at once. It finds the eigenvalues and the eigenvector. But it would be better, it'd probably be better practice for you to actually work out some of the characteristic equations just so you get better on your determinants. That's just my thought. But anyway, so there it is. There's our eigenvalue with eigenvalue 1. And then I had high hopes. I had high hopes that this calculator was also going to hack the complex eigenvalue. And sadly, as far as I can cipher, it does not. Now, that said, there do exist, I believe, I think the TI-89 probably can do that, but I'm not actually sure about that. I had one, I feel like maybe it didn't. Anyway, my TI-89 is long dead, and I'm certainly not going to spend that amount of money on an antiquated technology like a graphing calculator at this point. Anyway, let's see here. So, and so this is the matrix I need to row reduce to reveal what the eigenvector looks like. I'm trying to basically find the null space of this complex matrix. So the row reduction rules for complex numbers are the same as the row reduction rules for real numbers. And so I do some steps, and I do some more steps, and I do some more steps, and I did some more steps, and oh, look at that, I got the identity matrix, which means I made a mistake, because that means that the only solution to the original equation is 0. 0 is not an eigenvector, which means I'm either wrong about the eigenvalue or I'm wrong about this row reduction. I know I'm wrong about the row reduction. I don't know where the mistake is, but there's a mistake somewhere in there. All right? So there's that one. So I thought, all right, fine. I'll try it again. So I tried it again. All right? Here's my attempt number 2. This time I tried to do it for the conjugate eigenvalue. I thought, oh, maybe that'll make a prettier calculation. And it didn't. So here's my A minus the eigenvalue times I, which row reduces to this, which row reduces to that. I mean, I'm like, oh, wow, look, it's looking prettier. Yeah, well, it did look prettier. And maybe this would be right, but about this time, my Benjamin came home, and once Benjamin comes home and he begins his Benjamin activities, my calculational acumen it lowers significantly further. Although I've generally been making mistakes today, so like there's a certain time where I can do this calculation, and there's other times I can't. And this is nothing new. This is how I am. I've known this for years. Row reduction of explicit complex matrices is just not something I am calculationally adept at. So anyway, some of you might be able to hack it, but the complex arithmetic here is really quite onerous. Check this out. This has actually complex. Check it out. I go mode, complex. This is amazing. I can go like 6 minus 5i. There you go. That's a complex number. And I can actually, if I go shift complex and I go like 3, so this tells me that the radius for the complex number is square root of 61, and its angle in radians is that. If I went to mode and I went, shift mode, shift mode, switch back to degrees, I bet it would tell me the degrees. So let's see here. 3 plus 4i. All right, there's my number. I go complex, I go 3 like the angle and the radius and the angle. Check that out. So it's 5, radius 5, and the angle's 53.13. I think this will find standard angles and such. I'm sorry I didn't teach you guys this already. I'm just learning it myself. Like, anyway, so my point is I was using the calculator to do these things, and even so, even with the help of the complex arithmetic calculator, I still managed to mess it up, and I still managed to get back to the identity matrix, which only gives me 0, which means I'm wrong. I made a mistake again somewhere. What's the moral to the story? The moral to the story is sometimes you need to use technology. So I did. And so I got out my handy dandy MATLAB, and I put it into MATLAB, and out popped this calculation right here. So the row reduction of this matrix is that. And then I just used some common sense. See, MATLAB truncates decimals. So I undid it, right? This is like 7 plus 2/3. This is 11 plus 1/3. This is 3 minus 4. That's 4 2/3 I. So I converted all of those to exact fractions to make it prettier. So I've got this, that, and that. Put it all together. Here's what the row reduction looks like. So like, maybe in MATLAB probably could do exact fractions. I don't know. Maybe it can, maybe it can't. I really don't know. I'm sure Dr. Wang knows. But I am not Dr. Wang. Let's see here. And then, so yeah, so this is the honest to goodness exact row reduction of that complex matrix. And from that, I can read off the parametric solution like so. Boop, boop, boop. And since you see I've got a third, it's just nice to put w equal to 3 so we kill the fractions. So setting w equals to 3, I have finally my complex eigenvector u2 is minus 23 minus 9, 3 plus I times minus 34, 14, 0. And hooray! So yay for technology, right? So now, listen, if the robot apocalypse comes and all the calculators are evil and such, I'll find a way to do the calculation. But until then, I'm going to trust the computer for that one. So inevitably the question will come, do you expect us to do that on the test? And the answer is, well, of course. You guys are younger and smarter than I am, so yeah. I'm joking. I mean, you are smarter and younger, but one of these would eat the entire period. So if I give you a 3x3 with complex eigenvalues on the test, I have to be somewhat strategic and make sure that there's enough zeros in the matrix that it makes the calculation become much easier. But in principle, you should know what you should do. Even though in practice, for a matrix with lots and lots of non-zero numbers, it might just be beyond all of our arithmetic capabilities. All right. But anyway, here we go. This is what we found. We've found that this eigenvector has, for this eigenvalue, 5 plus 2i, we've got u is a plus ib, where this is a and this is b. This is the real part of the eigenvector. That's the imaginary part of the eigenvector. And just like I did today in class, we can take the complex solution and multiply it out and get the real and the imaginary part of the solution. And those are, by the argument I showed you in class today, separately solutions to the differential equation dx dt equals to ax. Three differential equations and 3 unknowns. They're all coupled. And as such, the solution is this: C1 times the real eigenvector part plus C2 times the real part plus C3 times the imaginary part. Now, if you're really paying attention, you might be wondering, what about the complex conjugate eigenvalue? Well, if I was to do the complex conjugate eigenvalue, all that would do, like 5 minus 2a has eigenvector a minus ib. And so if you go through this whole rigmarole, all that does is it switches, I think it's either the same solution or it's just off by a minus. I'm thinking it changes b to minus b, and it changes beta to minus beta. So you've got a minus and you got a minus. So this is the same. You've got a minus, and you get, so it literally is the same real solution, and it changes the imaginary part to minus the imaginary part. So in short, looking at the complex conjugate solution doesn't give you any new solutions. It's enough to find one eigenvector for a given eigenvalue. You get enough data there that you don't even have to look at the conjugate eigenvalue and the conjugate eigenvector. That's just how it works. It's a twofer. And there's the solution, right? And again, the book asks us to comment on the stability. So here we have positive exponential arguments. All of those blow up to infinity as t goes to infinity. So this would be like an unstable spiral as x, the absolute value of x would go to infinity as t goes to infinity, and it would be, if you were to graph it, it would be something like wee. All right, there's some pictures in the book like that. So in order to have a stable solution, you need all of your, if you have an exponentials, they all have to have minuses in them, all right? Or you could just have a pure sine cosine solution, then that would give you a bound orbit if it was like a two-dimensional problem. All right, so what's happening next? Your homework questions on Wednesday, and also I'll try to work some like 2x2 problems, which we can actually work the full way through even though they're complex, and those are usually what I end up testing on. But we shouldn't be scared of the bigger problems. We should just use technology. I hope that makes sense. And again, my apologies for today. So.